That's what it's called. That'd been fun.
Hello,
We
hello.
could.
How is everybody?
Doing good.
Sorry to be a little late. Traffic was really bad. No, just kidding. How's everybody this Friday? I see full class. That's pretty good. So as I emailed or sent a message on Canvas, it's okay if you submit your homework by Monday. It seems that especially number 4 is a whole lot of fun. Is that true?
Yes.
It is. It's a fun problem, though. You have to admit that. It's about Earth. Well, so what is difficult in that problem is that it's not Cartesian coordinate system or cylindrical, which is what we normally deal with, but it's actually spherical. So it's a little bit of a challenge. We haven't spent a lot of time doing spherical problems, but it's nevertheless important. So it's really just, it's the same shell balance. It's just that the shell is now a shell that is in the spherical coordinate system. So that's something to keep in mind.
And then, Professor,
Mm-hmm.
I was also having a lot of problems with the in-class assignment, and I'm not sure if other people were as well, but I could get the correct temperatures at the boundary conditions.
Mm-hmm.
So like at x equals b and x equals 0. But if I was at, say, b over 2, my temperature value was off by like 10 orders of magnitude. And I was just really confused.
10 orders of magnitude?
Yeah, like the temperature was 8 times 10 to the 10th.
That's a blow up. Okay.
Yeah.
Well, send me that little code.
Okay.
Did you check the formula I wrote in class against what's in chapter? I think it's 10.4.
Yeah, I tried it with both of them, but it still gave the same answer. So I wasn't sure what was going on there.
Okay, well, send me. How about send me? Because we can now theoreticize all we want.
Okay, thank you.
It's ultimately a piece of code. Yeah, not a problem if you need to submit. That was just, I'm never terribly upset about submitting on time, as long as you want to work on it. Submit it late, not a problem. Does that make sense?
Yes, thank you.
Question?
I had the same issue with that what's called the plotting for the in-class assignment. For my so I think what happened, and I think I figured out why the that BR coefficient was super huge. It was because if you use the units that it traditionally is in the book, like centimeters, you have to change it all to SI units, or the BR coefficient becomes like a super high because the VB is VB squared.
Okay, so that might be the root of the problem. You need to convert. I did mention convert to SI units.
Yeah. So that I didn't realize. I tried turning to SI units, and my BR became very low. But still, for the second equation, I still had problems plotting it. I got the first equation and looked kind of right from what you described in class, but the one where the T naught is the same on both sides. I tried doing it again, and I was getting problems with that.
Well, the second equation is actually slightly different because you cannot divide by TB minus T0. So you cannot use the same equation for both cases. That's why we wrote 2 different equations.
Yeah, I used the other equation that you used, and you said it should look like a quadratic, right? With the center having the high point?
Yeah.
So the thing is, when I use that second equation, though maybe I wrote something wrong in the code, but it went, it almost looked as if it was linear going from 70 Celsius going to 140 Celsius. Yeah. So I was getting very confused, but it looked like I changed the code correctly for the new one.
Yeah. Well, send me the code. All of this is theory until I actually see something. Like, it shouldn't blow up, but I don't know. I'll take a look. Like it should be, I mean, all of the, you shouldn't get all that. Viscous heating can be big, it cannot be all that big, right? It's not gonna blow up your system just from viscous heating, especially if you have both temperatures the same on both ends, then viscous heating is the only source of heat transport, right? So in its, just physically, it shouldn't be bigger than the other case. Yes? Okay, well, send me the code, I'll take a look. Don't worry about being late, just plot. This is just to kind of plot because we've been talking about these numbers sort of in an abstract way, so just to make them a little more real. And yes, the book or that particular problem uses different set of units other than SI, so convert to SI. I tend to prefer working with SI units, and my joke is always that who knows how many problems in industry are actually caused by the fact that we're not using the same. Not everybody's using the same system. So, anyway, all right. Without further ado, let's. Does everybody, before I start with the lecture, does everybody have any other questions? No? Okay. All right. This is not the correct presentation. We're going to do one more problem. Recent. And let me just check that I have enough pages here. Insert new slide. And a couple more, just in case. All right, and I'm gonna start on a new page. Funny, my computer immediately starts heating up and revving up. All right, so this problem is going to actually involve a porous medium, so which is why I'd like to solve it. And it's going to also, so from the physical perspective, it's going to also involve a chemical heat source, which is something we haven't had so far. Default choice of color is red, which one of these days I'm going to change, but apparently not today. So here's an example that is from your book, chapter 10.5. And this is heat conduction or with a chemical source. And the problem is the following. So I actually have a chemical reactor.
Dr. P, I don't think you're sharing your screen.
Oh, I'm talking to myself today. Let's fix that. Okay. All right. All right, how about now?
Yes.
Let me go to the correct. Okay. So we have, this is the part that I started presenting to myself. We have heat conduction with a chemical heat source. So I have a chemical reactor. Why does it? Okay. So I have a chemical reactor. It's insulated on top and bottom. And often, in order to enhance reactions, we need to increase surface areas because that's one way to actually speed things up. So this chemical reactor is filled up with spheres, and some of them in the first part, which is really there just to control. These are non-reactive. This is my sort of zone. I'm going to call that zone 1. And then in zone 2, this is where I'm going to actually change color. How about that red? So for reactive spheres, I'm going to throw in a red color. And they're coated. Okay. So this is my zone 2. It has reactive spheres. And again, the fact that spheres are coated, they increase the surface area where reaction can happen compared to just having the walls of this reactor. So that is in my zone 2. And then in the third zone, I again have just the regular spheres that are really just there to control the flow. So these reactive spheres, there's the reaction that is happening on their surface, and that reaction is source of heat. So basically what I have is that there is SC in joules per meter cube per second is rate of energy produced per volume. In this very moment, I'm not going to go into what is the functional relationship, but we're just going to assume that we have it. Okay, so this is something that is given. Now, I have a porous medium. So technically, I know that the way my fluid is flowing, and that's too complex to track. We're just going to really work with or model this as what's called plug flow. So I'm going to assume a constant or Darcy velocity, average velocity moving through this. So that's some sort of basically average that is based on the volumetric flux divided by this area on the other end. So I'm going to assume plug flow. So my fluid is moving with velocity. I'm going to denote that as a z direction with constant Vz, which is some constant V0, and it's equal to volumetric flux divided by area, if you remember our discussion of porous media flow. So this is my basically Darcy velocity. And what is fluid doing in between spheres? I'm just averaging that. So essentially, I'm going to treat this as a one-dimensional problem. I still have, or I can imagine this is sort of a cylindrical tube in z direction filled with these spheres, and I'm averaging everything with that z direction. So we're going to treat the problem as a 1D problem. So everything really depends on that z direction. So if you recall, when we do shell balances, okay, we need to just balance this. So I'm just going to basically do this in 1D. I'm going to still draw an area. Okay? And this is my Z. This is my Z plus delta Z. And this is my area, AZ. And it's the same on both ends. So this is area AZ plus delta Z is the same as AZ. So it's just some area across a cross-sectional area in this reactor. So if I'm balancing things just in one direction, I'm going to look at every balance goes what goes in minus what comes out plus whatever production I have within. At steady state has to be 0, right? So steady state balance, and we are balancing, recall this is heat transfer. So we are balancing our combined heat flux E, which in this case is really described just by EZ. So my in minus out plus whatever production, which I do have in this volume. And we are going to ignore, this is horizontal problem, we're going to go ignore any work of the outside forces like gravity. That has to be equal to 0. So what's coming in at this end at or boundary at Z for any small section of this reactor? Anybody? Nobody. It is Friday. Nobody wants to chime in. How about EZ evaluated at Z? So this is my energy flux. What do I have to multiply it with to get the actual amount of energy coming in to this, what I depicted as a cylindrical volume? Flux is rate per area. So I gotta multiply it by the actual area, correct? Is anybody listening? I feel lonely here on Friday. Yes? No? Times AZ is the area. That's this area that I drew here. I guess I'm gonna keep talking to myself. There we go. One person is listening. Thank you. Minus EZ on the other end is Z plus delta Z. Okay. Also times the same area. Again, this is 1D problem. Everything is the same on both ends. But what we have specifically in this region of reactive spheres, and I'm going to, because of that, write it in red, this production term is plus SC, and SC is rate of energy produced per volume. And the volume of this is this cross-sectional area AZ times delta Z. Does everybody agree with that part? So this is volume. And that all has to be equal to 0. Now this is in region 2. For regions 1 and 3, they have the same balance really. For regions 1, 3, balance is the same, with setting this SC to 0 because I don't have reaction. Okay. So technically, in terms of getting the equation, we're going to get a pretty general equation. So what do I do now with this balance? What's my next step?
Divide by the volume.
Excellent. We divide by the volume. So I'm going to divide everything. Divide. Okay. I'm going to start writing. Divide by AZ delta Z. Okay. So basically my AZ term I can immediately remove, and I'm going to have these first two terms, it's basically negative AZ at Z plus delta Z minus EZ at Z divided by delta Z. That reminds me of derivative. Okay, it's a finite difference. And plus SC is equal to 0. Okay, so I'm going to get back to my regular color. I'm going to get minus EZ plus delta Z divided by delta Z plus C is equal to 0. So when I take the limit and delta Z goes to 0, I'm going to get that minus CEZ DZ plus S to 0, or DEZ is equal to S. So that is for region 2.
Dr. Masha, I think your microphone's not working.
My microphone is not working?
Now it's working.
Ah, okay, so it really depends. So I need to kind of lean over my microphone is, I think, in the similar spot where the camera is. So I think I have to lean over a bit closer to it. Okay, so in regions 1, 2, remember SC is just 0. So the equation is even simpler in those regions. So it's, again, a relatively simple looking equation. My problem in this equation is that I didn't write what EZ is, and EZ can be quite complicated. So my EZ, I'm going to immediately write, this is that combined flux. I'm going to immediately write just its Z component is my 1/2 rho V squared, plus I'm going to use the enthalpy form, plus rho H hat times VZ. So this is the convective part with the pressure part added, which basically results in enthalpy here, plus the work, the Z component of the work of shear forces, and plus QZ. Now, this, I need to take a derivative of this, but let's take a look at it first. I'm going to do the simple part first, and that is the fact that tau ZZ is minus 2 mu dVz dz, correct? Does everybody agree with me? If you look up in the appendix, then that's what we get. However, well, Vz, I said this is the Darcy velocity, and I'm assuming I'm taking it in an averaged sense, okay? And I'm taking it as a constant, okay? Great. So if it's a constant, dVz dz is equal to 0, since Vz is that V0 and it's constant. Excellent. So this part disappears. I got rid of that. My QZ, oh, let me change the color. My QZ, okay, that term is my Fourier's law term, and it's typically of the form minus K dt dz. Now this is thermal conductivity, and it's thermal conductivity of the chemical reactor that is full of spheres. So this is going to have, I'm going to call this conductivity effective conductivity, okay? Because it's actually a porous medium. So it's a combination of fluid and solid spheres. So this is K effective is effective thermal conductivity of the porous medium within chemical reactor. And the way this reactor is set up, actually, it's also something that is it's a conductivity in the z direction. In other directions, I'm insulated, so technically, my conductivity or thermal conductivity is different in different directions. So that's something to be concerned about. But right now, I'm just going to assume, well, somebody has figured it out what it is, and it's some number that is given. If not, I can estimate it at the very least with those formulas that you have in your homework. There are some estimates available, even if they're not perfect or somebody has measured it. Excellent. And now let's go to the difficult term. There is this portion here that so far in all of our problems has actually disappeared, but today it doesn't. So I'm going to pick this color. Okay. My VZ is not necessarily 0. So this term, even when I take the derivative, is not going to all of it disappear. And I have specifically this enthalpy, which I haven't really told you, well, what do you do with it when you have to, you should have a formula for it. And you can look at the end of chapter 9 into details. I'm really just, this is from thermodynamics. It's essentially a mini review of your thermodynamics. The way it's estimated, this is it's a thermodynamic state, so it's described fully by pressure and temperature. Right? And the way we calculate it is, so this is enthalpy. Details at the end of chapter 9. But the way we will estimate it is with respect to a reference state at temperature T0 and pressure T0, which I'm going to refer to as a 0. So this is reference state. Because this formula was obtained by integration. So from T0 to T of Cp dt plus, oh, don't have space. I'm going to lower it down a little from P0 to P of V minus T dV dt. And I'm not going to go in details. This is just for you if you want to review your thermodynamics. What we're going to, in practice, use is the following integrated formula. So I'm going to assume for the temperatures that we have in the problem that my Cp is constant. So then the first integral is simple. It's really just T minus T0. And the second portion we're going to have as 0 in ideal gas, or 1 over rho, rho being the density, P minus P0 for fluids at given pressure P. And with constant, we are assuming constant density fluids. Okay, so this is what we're going to use as H. I'm going to do this. And this is, if you're putting together formulas for your next exam, this should go on there. Okay. You can also, let me actually find that quickly in the book, so you have the reference, the exact formula. You can also find, also refer to or bookmark BSL 988. Cool. So let's now plug that in. Okay. Now I have to do a derivative. What I'm really interested in is the derivative of EZ. Okay. And the derivative has, so this is what I'm trying to do. So this is the formula I'm trying to put this into. And then this is the second part of it. Okay. So what is my dEz/dz? I know that that's equal to SC, but I gotta work what is that dEz/dz equal to. So my dEz is equal to SC. What I intended to write. It's dEz of 1/2 rho Vz squared plus rho H0 plus I'm now multiplying that formula for enthalpy, which is right here. So my enthalpy H hat is H0 hat plus CPT minus T0. And then plus 1 over rho times P minus P0 because I have fluids here. Times rho. Let me erase. So I had, this is my essentially, let me write everything down. So this portion here is H. N minus K effective d square T dz. Remember this was the Q's d, whoops. This is derivative of QZ. All right. I will now give you a couple of minutes to work this out. Okay, so I want to sort of, you need to, there are certain terms, so I need to take derivative ddz, okay, of this term. And I want you to pay attention to the following thing. First, H0, that's a constant, so derivative of it will disappear. And my Vz is actually V0, and it's constant. Okay, so basically the derivative of both of these things will be equal to 0. So I want you to take that into account while taking this derivative. And I'm going to turn off the screen and let you do it for a couple of minutes. And then let me know what you get.
I have a question.
Mm-hmm.
It looks like when you substituted the H in, you multiplied VZ by the last term. Did you mean to multiply VZ on all the terms inside those brackets?
Yes. Let me see. Yes, that should be the case. Just a moment. Let's go back. That's an important point. Yes. So, no, I didn't multiply. So it's the, I multiplied this part. Let's actually correct that. Good point, good point, good point. Okay, so this is rho H0. So I did not multiply anything actually, except for this one. So I'm gonna do this. And then multiply it with VZ. So this portion here, it's not allowing. So this here is rho h. Okay. So I have, because inside the brackets, I'm supposed to have 1/2 rho Vz square, right? Plus rho h all times Vz. Okay. So I'll let you work that out for a couple of moments. So basically you need to clean that up and take a derivative and see what disappears because of the constants and what remains the same. What did you get? Anybody? Do you agree with me, disagree with me? No answer.
Why did the first 1/2 rho Vz squared go away?
Because Vz squared is constant and rho is constant. Take a derivative of constant. Question, right? So actually the entire first two terms, there's this term and this term are both constant. Even when I multiply this third term with Vz, I'm assuming Vz is constant. So my Cp hat rho VZ. The only thing that is non-constant here is temperature. So that's the only thing I take a derivative of. And same thing the second term. Pressure I can take a derivative of, but VZ is constant. Yeah? All
Yeah,
right.
that makes sense. Yeah.
So now we need a further simplification. If you notice, I have dt dz here, and I have dp dz here. Uh-oh. So in that case, so technically I have two things coupled with n. Okay. And I would need to go and search for pressure solution and whatnot. Well, I'm going to do the following. dp dz is a constant. Okay. We typically take pressure in these problems as a constantly applied across the system. But not only that, I'm assuming that if I'm controlling this system, my velocity is not very large. So VZ in itself, it's not large. And then what's driving the velocity, dp dz, is not very large either. So here I have two things that are relatively small and multiplied together. Okay. So I'm going to assume that this term is approximately 0. Now, that's something that needs to be checked, but this is now an assumption that I'm making. Okay. So basically, I'm assuming two small terms multiplied together. So that's practical also. That makes it practical for me to actually solve this. So then what remains here is Cp rho Vz dt dz is equal to K effective d squared T dz squared plus Sc. So this is the equation. And this is equation for zone 2. In zone 1 and 3, the same equation applies, but we can put Sc to be 0. Okay. And again, Vz is some constant, so this is basically, recall, Vz is assumed constant V0, and it's something that I know because I'm controlling the flow in this problem. But this gives me the temperature relationship. Now, for this, we also need boundary conditions, and this is 3 zones that are chained together. So basically, each zone at the ends, we have the temperatures given, and also we need to assume continuity of fluxes. And it's something that can be solved. We also need to have a form for Sc. So in order to solve this problem entirely, we need boundary conditions. Yes, somebody had a question? We need essentially 2 boundary conditions per zone. So pressure is typically measured at the very ends of zone 1 and zone 3. And then we also always have continuity of temperature as well as of flux at zone boundaries. We also need a form for SC. So that's something that needs to be given. Also need, also need a functional form for SC. And I'm not going to go into details of solving this. I just wanted to give one example where this enthalpy cannot be just disregarded. So just to go back to the picture, so basically I need a bond temperature here, then continuity of temperature here, continuity of temperature here, and I need temperature here. Those temperatures at the end I measure. And then we also have continuity of fluxes here. That gives me 2 boundary conditions per zone. Questions?
I also had one other question. Could you go back to the slide where you had DEZ over sorry, hold on. When you did the right before you did the differentiation. Yeah, right here. On this slide, the H minus H naught. What happened to the 1 over rho on the next equation?
I multiplied by rho because
Across
it's rho H.
uh
It's rho H.
I see. Okay. Got you.
So it's a bit of algebra here, really. But so conceptually, what you need is somebody has to give you the formula for H, which is what I gave here, in cases where we don't just let it disappear. And then there is actually some temperature dependence, or I get it expressed in terms of temperature right in here. And that gives me additional term in temperature right here. Also in terms of pressure. So I need some way mathematically to get out of it. In this case, I got out of it, well, physically, really, not mathematically. And I said, okay, these are 2 small terms that are multiplied together. So I'm going to assume they're small. Another option is say, well, dPdZ is something that I measure and I have it. I can assume it's constant. So I basically treat this as a constant and keep it in the equation. And then to actually close this, I need boundary conditions. Since it's 2nd order equation in temperature, I need, so ultimately this is going to be temperature Z profile. So I need 2 boundary conditions, right? And I need a form of SC that is a closed form of C. So I need to figure out a way to have a function for SC. Any other questions? So again, in terms of fluxes, these equations are deceptively simple. But then once I actually uncover what is my energy flux, then it can get pretty complex. Okay. All right. So one thing that I did not send you that I promised is the information on how to install Proctoria. What I'm going to do also as a test of sorts, I'm going to create a quiz that is going to be a dummy quiz. I'm just going to ask you to write something, scan it, and send it in. But I'm going to make a quiz out of it. So I'm going to basically go through to practice the entire process. The answer to the quiz will be very simple and will not in itself be graded, but you going through the entire procedure, I'm going to make it an assignment. So that way we will make sure that once we have the exam, that things are going smoothly and that technical part is going well. So I'm going to set that up over the weekend. Any other questions? No? All right. Well, I'm going to stay online if you need office hours.
Dr. Masha, can you talk about homework problem number 4?
Mm-hmm. Let me open it up. Okay. So we have Earth's inner core. It's right here. So this is my first sphere. And that has a radius of 1,200 kilometers. Then I have the outer core outside of this. That is, it goes up to 3,500 kilometers. And then mantle, and the very outer, is basically 6,370 kilometers. Okay, so we assume that this is a sphere, and okay, and then I also have 6,400 kilometers total. Okay, and I have a constant temperature at the outside, which is gross simplification, but we're going to use it. And these materials are all changing, and they have different thermal conductivities, K0, Km, Kc. Okay. Now, I need to establish the shell balance. Have you attempted to do that?
Yeah, I just don't know how to solve the boundary conditions.
So what did you get as a result of your shell balance?
I got
DDR of what is equal to?
VR.
DDR of VR?
No, I got T equals to negative C1 over K times R. Sorry.
So ultimately, just the shell balance, I'm balancing that energy flux E, and the only part, everything is static, so the only part that I have is Q, correct?
Yeah.
Fourier's law, yes. So DDR of R square Q should be 0. Did you get that?
R squared over Q.
R squared times Q.
I got DDR R squared times E is
Yeah.
0.
That's it. And
Okay.
your E is Q, correct?
Yeah.
Because you don't have any velocity. Well,
Uh-huh.
mantle is moving, but we're not looking into that. Okay, that'd be too complicated. So we are taking it as a thing sitting in place, right? So now basically all across all of these, you have that the derivative of R squared times Q, and Q is minus conductivity K times dTdr, yes. Now the problem in that is that your K differs in each of these materials.
Yeah.
Yeah. So you have to assume continuity of flux
Yeah.
across all of these. So this is very reminiscent. It's just a slightly different equation, but it's very reminiscent of what we were doing in the composite material.
Mm-hmm.
here, right? The only difference is that it wasn't just that dd, so instead of ddx of qx, I have ddr of r square qr is equal to 0. So what's constant is r squared times qr. Yes?
Yeah.
And my r is changing. Yes?
Yeah.
So basically, so r squared qr is constant across the system. So you repeat this problem, but you don't treat just one flux as just Q0. It's not Q0. It's R square Q that is constant and the same at every boundary.
Wait, what?
Excuse me.
So you need to put together, let me start writing. You need to put together two things. So you have something like this, right? Spherical system. And your DDR of R squared QR is equal to 0. Yes? Everywhere.
Excuse me. What,
Yes.
can you briefly explain where you're getting the R squared? Because I did my shell balance and I don't know. I got RQR.
Area depends on R square. Area in a cylindrical system, in the spherical system, right?
Yeah.
So you're going from area, so you're a piece of a little sphere, and you're going from R to R plus delta R, right?
Yes.
Well, this area at R is part of a surface of a sphere. So if you need to go to, let me actually find that in, do you have a book with yourself?
Yeah.
Okay. So you need to go to the spherical system in the back.
Because of this.
So there is this. There is a picture on page 840. It's way better picture than I can draw.
Okay. Yeah, I got it.
So you are in, do you see the spherical element?
Yeah.
So you're going from that element and you're going through the surface at the constant radius r to the surface. So there is a surface at the constant radius r, and you have a flux through it, and flux is a vector. So you got to multiply that QR evaluated at r with that area at r to the area at r plus delta r, or dr in this case, right?
Yeah.
And this depends on r square, right?
Yes. Yeah. I was confused. I don't know, for some reason I was thinking of it as a cylinder. So it makes sense now.
And then because you solved the problem with the cylinder just before that. So this is really equivalent to the problem 3, right?
Yeah.
Just for a spherical system. And because of that, you get this, right?
Oh, okay. Perfect. Thank you.
So essentially, in Cartesian, you get ddx of qx is equal to 0. Why? Because all areas are the same that are orthogonal to x, right?
Mm.
In cylindrical, you get DDR because, again, the cylindrical QR is equal to 0. And here you get DDR, or R squared QR is equal to 0. So this R is reflection of the fact that at every radius, the area differs. That's the whole problem with cylindrical and spherical coordinate systems. Areas change of these volume elements. If you're thinking about conservation, right? Let's say that you're injecting something or some reaction is happening at the middle of the sphere, which is basically technically what we're saying here. We have mantle that is a very high temperature, right? And stuff, so this is some super high temperature, it's a heat source in the middle of the sphere, in the middle of Earth, right? This stuff is coming out because the temperature on the outer part of this Earth is way smaller. We're talking from thousands, like 5,000 kelvins to 280, yes? So that heat is going, but as it's going, it's the same heat, the same amount of heat is going through areas that are increasing larger and larger and larger, right? But when you're conserving, our Q is described as per area, right? So as I'm going larger and larger and larger per area, I'm getting smaller and smaller and smaller because what's conserved is R squared times that per area part. Yes? Same in cylinder, if I was injecting in a cylinder. So if I'm thinking of well bores and injecting in well bores, whatever it is that I'm injecting, as I'm getting away from the well bore, I'm going to get smaller flux per area because my area is getting larger and larger. Yes? Make sense?
Yes.
So essentially in cylindrical coordinate system, that area is a function of R in times some length in Z direction, right? And in the spherical coordinate system, that area depends on R squared QR. So essentially, if you don't have a flow, like velocity of fluid moving around, and that contributing to the heat transfer, these are this, and this are three versions of your shell balance for three different coordinate systems. So that's what you always get. If you don't have any other, if you have some production terms or whatever, they might actually show up here in addition. But other than that, this is how balances look like with no production terms of any sort. Right? I'm just having things moved based on the temperature difference, and that's it. So then what the problem becomes is just matching things on the boundaries, right? Because QR, how does QR look like in spherical coordinate system? Do we know where we double check that? So QR in general, my Q is minus K gradient of T in any coordinate system, right? Does everybody present agree with me?
Yes.
All right. So how do I make sure that in spherical system does something weird doesn't happen for R? I'm looking at the QR, so R coordinate in spherical coordinate system. And all I want to double check is that there is no some odd term that shows up, and you double check that in Appendix A. I'm gonna get you the formulas in a second. So this is Appendix A for spherical coordinates. We are talking about table A73. So for gradient, we're looking at formulas D, E, F. Does everybody have a book open? So gradient of t, the r coordinate is indeed just dtdr, or in this case dtdr, because I don't have dependence on anything else. I just want to point the fact, which luckily will not mess with us, that theta coordinate is not just dt d theta in spherical coordinate system. It's 1 over dt d theta. Or 1 over r, apologies. And then phi coordinate is 1 over r sine theta, the dt d theta. So that's why I wanted to just to verify that indeed it's this simple. And luckily for r coordinate, it is. So now when I write that down, I have the ddr of minus k r squared dt r is equal to 0. And the problem is that this, I will have outer core, I have mantle, and I have, what is the third one, is KR or something like that. Right? So differs in different. So this is some big constant, right? This is constant for everything. It's just in one region I have to take K0, in another region I have to take Km, and in another region Kr, and I have to match the boundaries as I go out. Yes?
Yes, it makes sense.
And the rest is, well, quite a bit of algebra, really. And making sure you don't make a mistake. Is everybody else okay with that? So again, the problem is very simple to the composite material in the cylindrical coordinate system, as well as the linear. It's just that this r squared term gets things a little more complex.
Yeah, I understand that, but how do you solve for the boundary condition? I know there's continuity of
Temperature is
as well.
continuous, and this portion is constant.
Which portion?
This kr squared dt dr
Uh-huh.
is constant throughout the system, right? So woo, this is what we were doing. My slides are apparently really heavy as I, whoa, they even like, where did it go? Sorry. Do you still see my slides? Oh, I think my PowerPoint died. At some point, a lot of writing on top of PowerPoint kind of makes it a heavy file.
Then you can solve for t in terms of r, right?
Yes.
And then I don't know what to do. Like the solving the boundary conditions are kind of weird.
So basically you will just get 1 over r terms. So basically you put a chain like this. It's just that these are different radii for the core.
Yeah, I did that, but then there are like all kinds of different constants and how I don't understand how you can
So
solve
the way
them.
we dealt with it here is that these constants, you go and try to, basically I did this one minus this one, this one minus this one, this one minus this one, this one minus this one.
Uh-huh.
Okay.
And you add them up all together.
Yes.
Yeah, I did that.
So that's how you basically, and then you solve for what this constant that is constant throughout is there everywhere.
But, oh, the constant stayed the same?
Yeah, it's the flux that is constant throughout.
Oh,
R squared times Q is constant throughout. You can solve for that constant.
okay.
Yeah,
Huh.
because that's basically the trick with it in this composite material to begin with.
So you just found a way to cancel out all the C1, C2, and C3s, right?
Correct.
Okay. All right, that makes sense.
Yeah.
Thank you.
So it's a bit of a trick, but that's the same trick we applied in the composite material when we solved in class,
Yeah.
and also in that problem that I asked you to rework.
For the plotting question, do we like I got the same value. It blew up. So do you want us to just submit the code or?
Yes, can you send me that code? Because I'm not sure. It seems that I'm getting reports, so I'm gonna look into it. So just send me, and I'm gonna verify.
Email it to you?
Yeah.
All right, thank you.
Thank you.
All right.
Mm-hmm.
Thank you.
Mm-hmm.
Okay, I think I'm good. I was just gonna ask you about the quiz stuff. Actually, well, I turned in my homework already. I think I'm fine with it. I just kind of wanted to check if my
Yeah, I'm sorry, I didn't actually respond to your email. I got into something.
no, it's okay. It's fine.
If you want to, I can look at it. I didn't manage to look at it. If you want to update it, by all means, you can. Deadline is Monday, so whatever you submit by Monday will be taken as final.
Yeah. So basically for mine, I couldn't figure out how to rewrite it in just the K0 general form. Just like with the matrix. So I just plugged in the numbers and then got I did an 8x8 matrix. Basically, I had six equations that came from the temperature, and then two equations that came from flux, and then
there is nothing wrong doing it that way.
And then for the mantle crust boundary, I got 350 Kelvin, and then for the outer core mantle boundary, I got 5,300 something Kelvin. And so it seemed reasonable because it was in between.
That seems reasonable. Right now, I don't know numbers, but from the top of my head. But if they're in line with the numbers that are given, that's what you're going for.
Yeah, yeah.
Yeah. Those blow-ups that I hear about, though, in plotting the distribution, that's not okay.
I can I have it pulled up. If you allow me to screen share right now, I can just show you. I can show you my code.
Let me do that. Yeah, I forgot about that I can do that. Up. Okay. Let me just, I need to stop share and then try now.
Okay. It's very interesting. This is the first time, because we're using Zoom, we can do this now. For my fluids class, it's become very helpful because when we have problems with PVT sim, we can just show Dr. Acuna what we're talking about instead of sending screenshots.
We will change the way we teach because of this, even when we go back on campus.
Yeah.
Did you notice that? Let me quickly. And the technology has been around. We just haven't really used it. And now we'll get accustomed to it. And this is how we're going to do. Somebody was saying, and there is apparently a way, and actually let me try. So there is a way in this view options. So technically, I think it's the way the meeting is set up. You can set it up. So technically, I should be actually able to modify your code if you allow me to.
Oh, really?
No, how crazy is that? It's actually a little scary. But I could technically go and and I need to figure out what in the meeting. There's something about the meeting. If it's set up that way, you can let me modify anything, like as if I was sitting on your computer.
So Zoom has remote desktop. That's what you're saying, basically.
That's what I'm saying. Yes.
Yeah, my dad used to work with remote desktop like a lot. So he found it really funny that they didn't like it took them so long to switch over.
Yeah,
Or-
it's not. It's something that it has been there, and I knew it about remote desktops. I didn't know that you could do it through Zoom.
Yeah, I didn't know that
told
either.
me that it is possible. And all I know is that it's somewhere in the view options on top. It now tells me you're viewing Ruben Thomas's screen. And then in view options, all I can really do is do zoom ratio, exit full screens, things like those. But that's where it shows up as an option. I can annotate or like modify. I can even go modify what's on your screen. Yeah. So anyway. So yeah. So that's the part which is helpful for these kind of things. Okay. Anyway. So there is BR mu VB square divided the key T difference in temperature. Okay. So this is the case that the temperatures are different. So what do you get as a plot in that case?
Like this. Does that look about right? Or what you would expect? Also, this is in Celsius, not Fahrenheit. I had to convert
That's fine. You converted. Yes, that looks about right. And that's essentially how these contributions look like when you have different temperatures. Yes.
Yeah. And then when I plotted it for this one, I changed the code. Hold on, let me just fix it again. Nope, hold on. I have to go from the beginning.
Uh-huh. Well, what is your BR now?
So
recalculate BR?
This S is now that's the S is this. Yeah, sorry.
Okay.
Yeah. So basically it's the same thing, except in the equation, instead of the difference, it becomes T just T naught, right?
Yes.
Yeah. So I just called it S. Like S is insane.
Okay. So that is slightly different. So technically I used to have 150, so difference was 20, and now it's 100 or whatever it is, 70. Okay. 20 versus 70. So that shouldn't blow up in itself.
Yeah. So my code's not blowing up, but it's like this doesn't look like what it's supposed to be like 70 here and then 70 here, and then it's like a quadratic, right? That's what I assumed it was supposed to look like.
Yes. So let's look at the formula. Once again, so formula is in term. So if I put x is equal to 0, I'm just going to get a t0. If I put x is equal to b, you need to get 1 here. You know what I think? That x over b is extra.
Sorry, I couldn't hear you.
There's this x over b term.
Uh-huh.
That might be a typo in the book. Can you remove that x over b?
Yeah, let's try that. This one? You're talking about this one?
Uh-huh.
Oh.
You know why? Because like when you look at the formula, it has to disappear. That term on the left, it has to disappear for x is equal to b. And I think it's just hanging out there as a typo. And frankly, I got lazy, so I didn't solve for it myself. I just copied it from the book.
Okay.
I'm glad we
Okay.
plotted this. We discovered a typo.
You can send it in, right? I think they credit people who find corrections in textbooks.
You know, I have a pretty old book. So is this in your book as well?
Yeah, in my book, it had the same error. I checked your formulas, it matches the book. And then I had a feeling that the formula was wrong, so I actually looked up corrections for BSL, and I could not find a list of corrections. Like, I remember for my calculus book, they had corrections for
Because
some of
there
the...
is a revised edition.
Oh, there is?
There is a revised edition. So do you have second edition or second revised edition?
I have second edition, I think. Yeah, second edition.
Okay. So in revised edition, there might be. Okay. So I'm going to email the correction. Yes, that's what it is. Just like mathematically, it has to disappear at x is equal to b.
Can I
Otherwise,
just submit?
you're not going to hit T0. I mean, that's...
Yeah.
Yeah.
Okay, so do I need to do anything else on these plots, or is this fine?
No, that's it.
Okay, cool.
So I just wanted to get the feel, okay, you know, in the first case, when I have temperature difference and some viscous heating, somewhere in the middle of this lubricant, I might get a temperature increase of about 20 Celsius degrees or whatever it is in this case, 70 to 86, 16, right? And in the second case, where I only have viscous heating, so about half of it, right, is from just viscous heating, about 8 degrees in the middle is the maximum. Yeah. Is that a concern, right? That depends on the lubricant.
Yeah. What
so
happens?
My viscosity might change. So might start having viscosity as a dependence of temperature problem, which in some cases it matters and in some cases it doesn't. So these are all approximations, right? Okay, so yes, so we have discovered, yeah, I don't know, then blow-ups that are reported, I think it's probably a conversion problem. No,
yeah, it definitely is, because what I ended up doing was when I changed everything to divide by 100, but I only thought about this like at the middle of the night. I was done with it and I went to bed and then I was like, wait, what if it's because it's not in SI units and it's squared right here? And I was like,
right.
And then I came back real quick and then I divided everything and I was like, okay, that's what it was. And because
one thing that I keep thinking is how many blow-ups have happened because of the wrong conversion units.
No, but like
unit conversion in petroleum engineering specifically, because petroleum engineering is actually a stubborn industry that still keeps British units in most of the United States and Britain, and everywhere else they use SI system.
Yeah.
And frankly, British system drives me nuts because in SI system, I know everything is in 10 into a 10 into a 10 into a 10 when you need to roughly convert something in your head. And there's nothing that goes by any proper rule. Pounds and poundals and whatnot. Yeah.
Okay, awesome. That makes me happy that we figured that out. That was really fast.
Yeah, but the second thing that you can always do is actually just go and solve, because this was, conversion that was made and somebody was editing formulas and was just kind of carrying over the formula before, and X over B got left in.
Yeah.
Cut, copy, paste problem. We're all guilty of it. Okay.
Okay, thank you.
Well,
let me
you
exit.
can enjoy your weekend.
Yeah. How do I? Oh, okay. There. Stop. Sure.
There we go.
Okay. Have a good weekend. Okay. Bye.
You too.